Okay. In nature, the number of isotopes for a given element and their masses can be determined by using something called a mass spectrometer. And this is an instrument that J.J. Thomson used to discover the electron. And what happens is if you have a charged particle moving through a magnet, it will be deflected by the magnet based upon its charge to mass ratio, and then it will hit this detector on the other side. So this is an example of what a mass spectrometer looks like, and the kind of data that you can obtain from it looks something like this. So in this table, they're showing you the 3 different isotopes for neon, the masses of each, and their percent abundances in nature, which should add up to 100. Okay, so what do we do with this data? We use this data to calculate the average atomic mass for an element. And so those decimal numbers that you see, or fractional numbers that you see on your periodic table, that's where this comes from. So we're going to take a look at number 1, and I'm going to teach you how to calculate the average atomic mass for gallium. Okay, technically this should say average, which is based upon all of the different isotopes that are present for that element, okay? So here I've got gallium-69 and I have gallium-71. Now you may have 2, 5, 10 isotopes for a certain element, it doesn't matter. As long as we have the individual masses for each one and their percent abundances, I can calculate the atomic mass. So these are in percent. So that means before I use it, I have to move the decimal over 2. So move these decimals over 2 places to the left, and then we will use them in decimal form. So I'm going to take gallium-69. I'm going to take its mass, 68.9256. I'm going to multiply it by its percent abundance as a decimal, so it's 0.6011. And then I'm going to add that to the other isotope, which is gallium-71. So 70.9247 times 0.3989. Round these 2 places past the decimal, just like they are on your periodic table. You should get 69.72, and my unit would be U, or atomic mass unit. Okay. Now, the other type of question that you might get is question number 2. Question number 2 gives you 3 different isotopes for neon, gives us the mass numbers and the charge, and it asks us which one will be deflected the most and which one will be deflected the least. Well, this is based upon the charge to mass ratio. So the one that is deflected the least will be the heaviest, and then deflected the most will be the lightest. Okay, so the most deflection will have the lowest mass number. Which one would that be? 20. Yeah. So when you read these, this one would typically be read neon 20. This is neon 21, and this is neon 22. So I'm going to move this down, and then under most deflection, we're just going to write the neon 20. And then the least deflected would be which one? Yeah, neon 22. So that means you would put the neon 21 in the middle. Okay. All right, and then I have one last problem to do before I let you loose on your homework. This homework assignment is going to be due at 12:30 because I want you to finish it in class. Okay, so let's come down here. Number 3 is kind of an advanced problem using basic algebra, and let me explain why. So here it says that we've got 2 isotopes for chlorine, chlorine-35 and chlorine-37. They give us the corresponding masses. They want us to calculate the percent abundances for chlorine-35 and chlorine-37 using the data. Then they gave me the average atomic mass for chlorine, which we would need to use, okay? So what this means is we would probably assign a variable for chlorine 35. I'm going to label it as X, and the other one should be Y, but we can only have one variable in our equation. So X plus Y should add up to 1 if I was thinking of them as the decimal version of the percent abundances. So that means Y would be 1 minus X. So I'm going to be using this and this when I attempt to solve for their percent abundances. So I'm going to take the mass of chlorine 35, which is 34.9689. I'm going to multiply it by X, which would be its percent abundance as a decimal. I'm going to add that to chlorine 37 times 1 minus X, which would be its percent abundance as a decimal. This will add up to the average atomic mass for chlorine. And we'll solve for X. Okay, so here we need to distribute this, and then everything else should be pretty smooth sailing. Right, we would, I forgot the little X right here. We would then combine the X's, which would be these. And then I'm going to subtract this 36 from both sides. I'll end up getting a negative value, so this cancels. And this is negative 1.5129. And then I'll divide both sides. This will cancel, and I will get X is equal to 0.75. What this tells me is that if you multiply this by 100, that's 75%. Okay, so this chlorine 35 is 75%. Obviously, that means the other one would be 25%, because the percentages need to add up to 0. Okay, now I want you to look at your atomic mass periodic table so I can teach you a trick before you work on your homework. If you take a look at your atomic mass periodic table, I want you to look at carbon, okay? Carbon has got a decimal of 12.01 underneath it, right? It's its mass, its average atomic mass, okay? Whatever whole number this is closest to, that's the most abundant isotope in nature. So carbon 12 would be the most abundant isotope for carbon in nature, okay? If I was doing the same thing for oxygen, oxygen is 16.00. Which one is most abundant in nature?
Oxygen 16.
Oxygen 16, exactly. If you look at nitrogen, nitrogen is 14.01. Which one is most abundant?
14.
Yeah, nitrogen 14. Easy, right? Okay. All right, so the homework is open. It's due at 12:30. When I do 5.2 through 5.4, we're just gonna probably do it all at once, because it all goes together and there's really nothing much in 5.2 and 5.3 to talk about, okay?